In this video, I have presented valuable information required to select and utilize of a waveguide. Consider to have a rectangular waveguide with the dimension of A and B. The cutoff frequency for this waveguide is specified as this equation. Actually, the cutoff frequency is the lowest frequency for which a mode will propagate in the waveguide. In another word, at frequencies larger than cutoff frequency of a mode, the waveguide has minimal attenuation for that mode. Since A is larger than B, the first mode for this waveguide is TE10 and the second mode is TE20. The best working frequency of a waveguide is the range where the first mode is excited and the second mode is not excited yet. Since as the modes are increased, the power of the wave should be divided between them and the efficiency of the waveguide is decreased. So, for rectangular waveguide, the bandwidth will have such range. As it can be seen, the bandwidth is 1 octave. The electric field for TE10 is as shown here, and for TE20 is as shown in this figure. Actually, at the lower frequencies than the cutoff frequency, the cross-section of the waveguide is smaller than the wavelength, so the frequency cannot be propagated. Now, check a standard waveguide as WR90. The dimensions are as shown here. Actually, the standard range for operation of the waveguide is between 125% of F10 and 189% of F10. So, the recommended operation frequency range for this waveguide is between 8.2 and 12.4 GHz. The first propagating modes for rectangular waveguides are shown in these figures. In the next step, we are going to simulate them. To create a suitable project, I use microwave and RF template. Then I select circuit and component. In the next step, I choose waveguide and cavity filter workflow. Then I press next and I use frequency domain solver. In the next page, I change the units and then I press next. Since I want to simulate WR90, I set the frequency range as it covers, expand, and also more than one mode can be propagated in the waveguide. I set 2 as minimum frequency and 30 as maximum frequency. For monitors, I choose E field, H field, and surface current. I press finish to close the window. I define the dimensions of WR90 in parameter list section. In this template, the background is filled by PEC material. We can change it from material type scroll, but here it is not necessary, since it is enough to see the modes inside the waveguide. So I am going to create a vacuum region as a waveguide. I use cube from modeling header. I set vacuums as its material. In the next step, I set PEC as its walls by defining proper boundary conditions. I select boundaries from simulation header. I set electric boundary condition for the waveguide walls, since I will insert excitation for input and output of the waveguide. It is not important which one of the boundaries will be utilized. Here I set open boundary condition for these walls. To excite the waveguide, I specify the input value using picked phase. In the next step, I excite the waveguide using waveguide port from simulation header. In the open page, I increase the number of the modes to 4. Then I press OK. I do the same procedure for the back wall. Then I press Frequency Domain Solver. In order to decrease the simulation time, I only excite one port as a source type for almost. Then I press Start to do simulation. To see results, I click on S parameter from navigation tree. To have better view, I select only S21 for all modes. So I do right click on the result, then I choose select curves option. And then I select the purpose curve. I use X marker to read the cutoff frequencies. The first cutoff frequency is about 6.6 GHz. The fourth cutoff frequency is about 16.14 GHz. In the next step, I'm going to check the electric field, magnetic field, and surface current from 2D results in the navigation tree. The monitor frequencies include 2 GHz, 16 GHz, and 30 GHz. 2 GHz is lower than the cutoff frequency of the first mode, so none of the modes won't propagate it at that frequency. Sixteen GHz is lower than the cutoff frequency of the fourth mode, so fourth mode will not propagate it at that frequency. 30 GHz is higher enough for all of these four modes to be propagated. The same analysis is available for magnetic field and surface current. I hope you to like this video. Please like it and subscribe me for more. Thank you.